A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Imagine a classroom in 2035. You walk in, and you don't see students hunched over physical textbooks or scratching out long division on a chalkboard. Instead, they're wearing haptic gloves, staring into augmented reality displays, and they aren't just solving a static math problem. They are currently tasked with designing a localized countermeasure for a simulated swarm of autonomous drones that just changed its flight pattern. They are literally adjusting the PID controllers and the sensor fusion algorithms of a virtual interceptor in real time to account for a new atmospheric variable the teacher just injected into the simulation. This isn't just a cool tech moment, it's a survival mechanism.
That is an incredible image to start with, Corn, and honestly, it's not as far off as people think. If we're looking at the landscape of national security and technological superiority, the old drill and kill method of just memorizing formulas is basically obsolete. We're moving into an era where the speed of innovation is the only real armor a country has. Today's prompt from Daniel is about exactly that. He's asking us to go deeper into how we actually design a curriculum for the next generation of tech and physics talent in Israel. He wants to know how we balance that deep, unyielding technical rigor with the kind of outside-the-box ingenuity that has historically given Israel its edge. By the way, today's episode is powered by Google Gemini 3 Flash.
Yeah, Daniel really put the pressure on with this one. Here is exactly what he wrote to us. We've talked before about the importance of rigor in STEM subjects for ensuring that Israel maintains a technological edge over adversaries. However, we need to go deeper. If you were devising the curriculum for the next generation of talent in technology and physics, what would you emphasize to ensure they have both the technical know-how and the ingenuity to think outside the box?
Herman Poppleberry here, and I'm ready to dive into this. This is a massive question because it touches on the dual mandate of education in a high-stakes environment. You need graduates who have the mental calluses to handle brutal mathematics, but if they can't apply that math to a wicked problem with shifting requirements, they're just calculators, and we have plenty of calculators now.
Right. And as AI starts to handle more of the standard engineering tasks, the human element has to shift toward where the AI struggles, which is often that messy intersection of physics, adversarial intent, and limited resources. We can't just teach kids how to use the tools. We have to teach them how to build the tools while the room is on fire. So, Herman, where do we start? If we're building this curriculum from the ground up, what's the first pillar?
The first pillar has to be what I call computational physics and simulation literacy. We have to move away from the idea that physics is a series of static equations you solve on a piece of paper for a perfect, frictionless vacuum. In the real world, there is no vacuum, and there is definitely friction. The shift we need is from analytical solutions, where you find the X on a page, to numerical methods and dynamic modeling.
Tell me more about that distinction. Because I think most people hear physics, and they think of Newton's laws or Einstein, but they don't necessarily think about it as a computational exercise.
Think of it this way. An analytical solution is like a poem. It's elegant, it's precise, but it only works for very simple systems. Once you add three bodies interacting, or turbulent airflow, or a missile that is losing mass as its fuel burns while being buffeted by crosswinds, the poem breaks. You need a computer to crunch the numbers in tiny steps. That's a numerical method. The problem is that many students today use simulation software as a black box. They plug in numbers, hit run, and get a pretty colored map. But if they don't understand the underlying finite element analysis or computational fluid dynamics, they won't know when the simulation is lying to them.
And that's a massive vulnerability, right? If you're designing a system like Iron Dome, and you're relying on a simulation that has a tiny rounding error or an unexamined assumption about atmospheric density, your interceptor misses by a meter. In missile defense, a meter might as well be a kilometer.
Precisely. Well, not precisely, because I'm not allowed to say that word, but you hit the nail on the head. One of the most interesting developments we've seen recently is the release of SimShield in January 2026. It's this open source defense simulation platform that some of the tech units are using now. A proper curriculum would have 16-year-olds breaking SimShield. Not just using it, but looking at the source code, understanding how the integration steps are calculated, and realizing that if the time step is too large, the simulation of a high-speed projectile becomes physically impossible.
But how do you actually teach that to a teenager without their eyes glazing over? If you start talking about time steps and integration errors in a vacuum, you lose them.
You don't teach it in a vacuum. You teach it through sabotage. You give them a model of a bridge or a drone that should work according to the math, but you've secretly introduced a ghost in the machine, a floating point error, or a misaligned sensor coordinate. Their job isn't to build the thing, it's to find out why the perfect math failed in the simulation. It turns the student into a detective of the physical world.
So, you're saying the rigor isn't just doing harder math, it's understanding the relationship between the math and the silicon. It's knowing that the computer is just a very fast, very literal idiot that will follow a flawed equation right off a cliff.
That's a great way to put it. The computer is a fast idiot. To be a broad spectrum scientist, which is what programs like Talpiot aim for, you have to be the one who understands both the physical constraints of the world and the logic systems we use to manipulate it. You can't just be a coder, and you can't just be a physicist. You have to live in the gap between them.
I love that. But it brings up a tough trade-off. There are only so many hours in a school day. If we're spending all this time on computational modeling and simulation literacy, are we losing the foundational pen and paper math that builds that mental discipline? You mentioned mental calluses earlier. Do you get those from staring at a screen?
It's a delicate balance, but I'd argue that the calluses come from the struggle, not the medium. If you give a student a problem that cannot be solved with a standard formula, something where they have to iterate, fail, adjust their model, and fail again, that builds way more resilience than solving 50 identical calculus problems. We need to move toward inverse engineering. Instead of saying, here is a lens, calculate the focal point, we should say, here is a blurry image of a target 5 kilometers away, design the physical and digital system required to clear that image using only these 3 specific materials.
That sounds like a nightmare for a student who just wants to get an A and go home. But I guess that's the point, isn't it? We aren't trying to produce A students. We're trying to produce problem solvers who don't panic when the textbook doesn't have the answer in the back.
Right, and this leads directly into the second pillar of this hypothetical curriculum, adversarial thinking and constraint-based design. In most STEM programs globally, you're taught to solve for efficiency. How do we make this bridge the strongest for the least amount of steel? But in a national security context, you aren't just fighting gravity or wind. You're fighting an active, thinking opponent who wants your bridge to fall down.
So, red teaming for high schoolers?
Essentially, yes. We should be integrating adversarial logic modules into physics labs. You know how the Maximum program, the National Cyber Initiative, added those modules in late 2025? We need that for physical engineering too. Imagine a lab where half the class designs a communication protocol for a drone, and the other half of the class has to figure out how to jam it using basic radio components. Then they swap.
That is brilliant because it changes the goal of the student. They aren't trying to please the teacher, they're trying to beat their classmate. It taps into that competitive drive and chutzpah that we always talk about. It's not just about, is this right? It's, is this robust enough to survive someone actively trying to break it?
And that forces you to think about second-order effects. If I harden my sensor against jamming, does that increase the power draw? If the power draw goes up, does the heat signature make me more visible to infrared tracking? This is what I mean by wicked problems. These are problems where every solution creates a new problem. Traditional education hates wicked problems because they are hard to grade. But those are the only problems that actually matter in the 24s and 25s of the real world.
Wait, can you give me a concrete example of a wicked problem in a classroom setting? Like, if I'm a teacher, what do I actually hand out on Monday morning?
Okay, here's one. You give the students a small, off-the-shelf electric motor and a limited battery. The assignment is to build a cooling system for a high-intensity laser that will be mounted on a moving platform. But here's the kicker. The cooling system itself cannot weigh more than 200 grams, and the platform will be operating in an environment that is 50 degrees Celsius. If they use a fan, it draws too much power. If they use a heat sink, it's too heavy. If they use liquid cooling, the pump might fail under vibration. There is no correct answer in the back of the book. There is only a series of trade-offs. The student has to defend their specific set of compromises against a red team of students who are trying to find the one condition where that cooling system fails.
You mentioned grading, and that's a huge hurdle. How do you grade someone's ability to think outside the box without it becoming totally subjective? If a kid comes up with a completely insane, non-linear solution to a physics problem that technically works but doesn't follow the lesson plan, does the system reward them or penalize them?
That's where the productive failure model comes in. The Ministry of Education and the Innovation Authority have been talking about this 40 million shekel initiative to reward failure in experimental physics. The grade shouldn't be based on whether the circuit worked on the first try. It should be based on the quality of the failure analysis. If your drone crashed, tell me exactly why. Show me the data logs. Show me 3 different ways you could prevent that specific failure mode in the next iteration. That is how you build a scientist. A scientist who is afraid to fail is just a technician.
It's funny, we're talking about high-stakes tech, but this actually sounds very old school, in a way. It's like an apprenticeship where you're expected to get your hands dirty. One of the points Daniel mentioned in his notes was about field immersion, the idea that you can't just study these things in a vacuum. You have to see where the problems actually occur.
Yes, that's a huge part of the Talpiot model. They take these kids, and they are basically kids, 18 or 19 years old, and they send them to the mud with the infantry or onto the deck of a missile boat or into a cockpit. You can't design a better interface for a tank commander if you've never felt how much a tank shakes when it's moving over rocky terrain. A next-gen curriculum needs to bridge that gap between the clean lab and the dirty reality.
How does that work for a civilian high school, though? You can't exactly send a group of 10th graders to an active artillery range for a field trip.
You don't have to send them to a war zone. You send them to a construction site or a hospital's power plant or a municipal water treatment facility. You tell them, your job is to identify 3 single points of failure in this system that a physical or cyber adversary could exploit. It grounds the abstract physics in the physical infrastructure of their own neighborhood. When you realize that the water coming out of your tap depends on a specific pressure valve that follows the Bernoulli principle, physics stops being a chore and starts being a superpower.
I'm thinking about the 8th grade strategic bottleneck that Daniel mentioned. The idea that if you aren't tracked into the advanced math and physics by age 14, you're basically out of the running for these elite units. That feels incredibly rigid for a culture that prides itself on being outside the box. If we're building a curriculum for the future, should we be looking for those late-blooming geniuses who maybe didn't love math in the 7th grade but have an incredible intuition for systems?
It's a tough one. On one hand, the mental calluses take time to build. You can't just wake up at 20 and decide to be a world-class physicist if you don't have the foundational arithmetic and logic locked in. But I do think we focus too much on performance and not enough on potential. There's a risk that we're selecting for good students rather than great innovators. A great innovator might be the kid who is bored to tears by a standard algebra test, but spends all night building custom mods for a flight simulator.
Right. The kid who is currently failing history because he's busy teaching himself how to optimize a neural network on a Raspberry Pi. We need a way to catch those kids. Maybe the entry point for the advanced track shouldn't be a single test score, but a portfolio of projects. If you can show that you've solved a complex, constraint-based problem, even if you did it in your garage, that should count for more than a perfect score on a standardized exam.
I love that. A proof of capability rather than a proof of memorization. And it would help with the strategic goal of integrating different sectors of society too. If you're a Haredi student or someone from the periphery who maybe didn't have the same secular foundation, but you have a high analytical capacity from years of intense religious study, you might have that system-level thinking already. You just need the right bridge to translate that into physics and code.
So, let's recap the Korn and Herman curriculum so far. Pillar 1, computational physics. Stop treating the computer as a magic box and start treating it as a tool that you have to understand at the code level. Pillar 2, adversarial design. Everything you build should be tested against an opponent. Pillar 3, failure as a metric. You are graded on how well you analyze your mistakes, not just how well you follow the instructions.
And don't forget the inverse engineering aspect. We need to stop giving them the formulas and start giving them the symptoms of a problem. If the goal is to maintain a technological edge, we have to realize that our adversaries are also getting better at standard engineering. They can read the same textbooks we can. The edge comes from the things that aren't in the textbooks. It comes from the chutzpah to challenge a technical assumption even when it's coming from a superior.
That's a huge cultural point. In elite units, a lieutenant can and should tell a colonel if a technical plan is flawed. How do you teach that in a classroom? Most schools are built on the idea that the teacher is the source of truth and the student is the recipient. That is the literal opposite of the innovation mindset.
We should have critical inquiry sessions. A teacher presents a perfect technical solution to a problem, and the student's job is to find the flaw. And the teacher should deliberately hide a flaw in there. It trains the students to never take a technical claim at face value. Trust, but verify is for diplomats. Engineers should distrust and simulate.
Distrust and simulate. I want that on a t-shirt. But okay, let's talk about the AI in the room. You mentioned at the start that this script is written by Gemini. If AI can now write physics-based code and solve complex differential equations in seconds, what is the value of a human engineer in 2040? If I'm a student today, why am I sweating through these mental calluses if an LLM can do the math for me?
This is the most important question of all. The value of the human isn't the doing, it's the framing. AI is incredible at finding the answer to a well-defined question. It is still quite poor at figuring out what the right question is, especially in a novel, high-stakes environment where the rules are changing. The human is the one who notices that the sensor data feels wrong because of a subtle environmental factor the AI hasn't been trained on yet. The human is the one who understands the intents of the adversary, not just their tactics.
So the curriculum needs to emphasize problem framing. Here's a messy situation. Tell me what the actual physics problem is. Once you've framed it, sure, use the AI to help solve it. But if you frame it wrong, the AI will just give you a very precise answer to the wrong question.
I mean, you're right. If you ask an AI to design a shield for a satellite, it will give you a great shield. But it might not realize that the adversary isn't going to hit the shield. They're going to use a laser to heat up the satellite's fuel lines until they expand and leak. The human engineer is the one who thinks about the unintended attack vectors. That kind of creative, paranoid thinking is very hard to automate.
Paranoid thinking as a skill set. I love it. It's basically pre-mortem analysis as a lifestyle.
It has to be. If you look at the Shield of the Levant or the iron beam laser systems, those didn't come from people following a standard curriculum. They came from people who looked at the physics of light and the physics of ballistic trajectories and said, what if we did something that everyone says is too expensive or too difficult? They pushed the boundaries of the physically possible by understanding the constraints better than anyone else.
How do you balance that pushing boundaries with the sheer danger of it? If we're encouraging kids to be paranoid thinkers and rule breakers, how do we ensure they don't accidentally blow up the lab or the national grid?
That is where the rigor comes back in. You can only break the rules once you have mastered them. You can't think outside the box if you don't know exactly where the walls of the box are. The curriculum has to be a sandboxed freedom. You give them a safe environment, like a high-fidelity simulation or a restricted local network, where they can be as destructive and creative as they want. But the moment they step into the real world, they have to carry the weight of the professional ethics of engineering. It's like being a surgeon. You practice on cadavers and simulations so that when the real heart is on the table, you don't have to guess.
And that brings us back to quantum intuition. Daniel mentioned that by 2026, we're seeing superposition and entanglement being taught in high school. That feels like a massive jump. I remember struggling with basic electromagnetism in high school. Now we're asking kids to have an intuition for things that literally defy common sense.
That is the goal. If you wait until graduate school to learn quantum mechanics, your brain is already hardened into a classical worldview. You think things have to be in one place at one time. But if you start learning the logic of quantum systems at 14 or 15, you develop a different kind of intuition. You become a native speaker of the subatomic world. And when we finally have scalable quantum computers, which is the next big battlefield, those kids will be the ones who can actually think in quantum algorithms.
It's like learning a second language. If you learn it as a kid, you don't have to translate it in your head. You just speak it. We're trying to create quantum natives.
That's a perfect way to describe it. We're preparing them for a world where the very nature of computation is different. If we don't do that, we're training them for a war that's already over.
So, we've covered a lot of ground here. We've got the technical foundations, the adversarial mindset, the embrace of failure, and the push into quantum and AI. What are the practical takeaways for people listening? Because not everyone is designing a national curriculum, but plenty of people are educators, or parents, or students themselves.
For educators, the big one is integrate failure analysis into everything. Don't just grade the result, grade the postmortem. If a student's project fails, that should be the beginning of the lesson, not the end of it. And stop giving them clean problems. Give them dirty ones with missing data and conflicting goals.
And for parents and students, I'd say seek out project-based learning that has real-world constraints. Don't just focus on the test scores. If your kid is building a complex system in their room, even if it seems like a toy, encourage them to document their failures and their pivots. That metacognition of understanding your own problem-solving process is the real edge.
And for the policymakers and the system, I think we need to be braver about breaking the 8th grade strategic bottleneck. We need more on-ramps for talent. We can't afford to lose a single brilliant mind just because they weren't ready at age 14. The competitive landscape of 2026 and beyond is too tight. We need everyone.
Including the late bloomers and the outsiders. I think that's a really powerful message. Innovation isn't just for the people who are good at following rules. In fact, it's usually for the people who are slightly annoyed by the rules.
Slightly annoyed is a polite way of putting it. But you're right. The chutzpah to say the textbook is wrong, or the kernel is wrong, or there's a better way to do this, is the engine of technological superiority. Our job as educators and as a society is to provide the rigor so that when they do challenge the system, they have the data and the physics to back it up.
It's the difference between a rebel and an innovator. A rebel just breaks things. An innovator breaks things and then builds something better in the wreckage.
I love that. And that's what this curriculum is designed to produce, disciplined innovators. People who respect the laws of physics but have no respect for the way we've always done it.
Well, I think we've given Daniel a lot to chew on here. It's a vision of education that is as much about character and mindset as it is about Maxwell's equations. Before we wrap up, I want to mention that if you're interested in the physics side of this, we did an episode a while back, episode 147, where we did a technical deep dive into the physics of Iron Dome. It's a great example of what happens when this kind of ingenuity meets rigorous physics.
That was a fun one. It really shows how you have to account for everything from radar cross-sections to the burn rate of solid rocket motors. It's the broad spectrum stuff in action.
You know, thinking about that episode, one thing that stood out was the human-in-the-loop problem. Even with all that automation, a human still has to make the final call in seconds. Our curriculum needs to train for that specific moment of high-pressure decision-making.
We should have stress labs. You're solving a complex differential equation, but every 30 seconds, someone changes the parameters or tells you that the power grid just went down. You have to learn to maintain your technical clarity while your adrenaline is spiking. That's the mental callus in its purest form.
All right, we're coming up on our time. This has been a fascinating deep dive. It really makes you think about what the human value add is in an increasingly automated world. It's that ability to bridge the gap, to think like an adversary, and to thrive in the wickedness of real-world problems.
And to stay curious. If you stop being curious about why things fail, you stop being an engineer. You just become a user. And users don't maintain technological edges.
Well said, Herman Poppleberry. Big thanks as always to our producer, Hilbert Flemingtop, for keeping the gears turning behind the scenes. And a huge thanks to Modal for providing the GPU credits that power the AI systems we use to generate these scripts and run our simulations. This has been My Weird Prompts.
If you're enjoying these deep dives into the intersection of tech, security, and education, We'd love it if you could leave us a review on whatever podcast app you're using. It really helps other curious minds find the show.
You can also find us at myweirdprompts.com for our full archive and RSS feeds. We'll be back soon with more of Daniel's weirdest prompts. Until then, keep breaking things and then analyzing why they broke. Take it easy. This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird